Okay, should we start?
Let's start.
Okay, Harry, on integration and scaling is extremely important in the last stage of before you start solving structure.
Right. Okay, that's what I'm going to talk about. That's me, that's what the course is, that's what today's date is. Okay, why are we doing the X-ray experiment is a really important question to answer, to think about before you collect the data. What we're doing is we're measuring the intensities of the diffraction spots on our images so that we can get their structure factor amplitudes. That's given in the first equation. And the reason why we want to do that is because we want to get the electron density out. The electron density is what gives us our structure. Forget about the nuclei, it's the electrons we're after. And we can only do that using this equation if we have our values for F. So it's very important to get good values of F. One thing you'll notice is that every single reflection affects every single point in real space of the electron density as well. So you try not to miss the reflections because you may be missing some useful information. The last couple of lines are self-explanatory, so if you do your careful data collection, measure your intensities carefully, then you can get the phases back by some means, and other people will talk about that later. Okay, Phil went through this the other day, and it's really important to stress this through the whole thing. When you're collecting your data, don't just go blindly into it. Have a look at the images as you get them. If you can, pre-process some of the data before you start so you get an idea of what the crystal parameters are, you know, the A, B, C, the alpha, beta, gamma, what the crystal orientation is, and perhaps get an idea of what the Laue group is. Get an estimate of the mosaicity, so you can tell to start off with if you've got a very mosaic crystal or a very single crystal that lacks mosaicity. Get an idea of what the effective resolution limit is, so you put your detector in the right place. So don't have the detector too close, so you've got great swathes of the detector on the outside that have no spots on them, and similarly don't have it too far back, so that you're only collecting the low resolution data. Get the exposure time right. Don't collect for too short, so you can't see the intensity even if you're strong reflections. Don't collect for too long, so you've got overloads on your image. These strong reflections are beyond the dynamic range of your detector. And it's always worthwhile spending some time to get a strategy for your data collection. Now, I'll assume that most of you are biologists, you work in the lab, and you spend weeks or months or sometimes years to get the crystals you're going to be collecting data on. Now, if you go to Diamond at the moment, collect data on a hot beam line with a Pilatus, you can get a complete data set inside a minute without thinking about it. And that data set may just be crap. When you spend weeks or months or even years getting your crystals, isn't it worthwhile sitting down and spending 5 minutes to get an idea of how to collect the best data possible from your crystals? It really is. No matter what data processing program you use, can get information out of rubbish. So Mosfilm can't, XDS can't, Star Trek can't, HKL can't, none of them can. If you've got good information on your images, you make your life easy and you can choose which data processing program you want to use then. And they all work about as well as each other. The last point, don't necessarily believe what your PI or the postdoc who goes with you says. Have a think about it. It's your experiment. It's your work. It matters more to you than it does to them. Your PI will have other students later. Even beamline scientists get things wrong. And then at Diamond or ESRF, use the tools that are available. Use something like Edna if you've got it there. Okay, so you collected your data, have a look at the images. Have you got any spots on the images? If it's completely blank, and you may want to zoom in if it's a Pilatus, because very often the spots are very, very small and they're hard to see with a zoomed out image. But have a look at it, make sure you've got spots on the image. If you've got no spots on the images, don't waste further time on it. perhaps think about how you collected the data to get to having no spots there. Have you used the detector efficiently? So have you used more or less the full surface area of the detector? Do the spots look reasonable? Now, so are they split? Are they huge spots? Are they above background mostly? Can you see the separate lunes? If you can't see separate lunes, then that suggests that your mosaicity is perhaps very large. Is there only a single lattice? Well, if you've got more than one lattice, it's still quite difficult to process the data, even with all the work we've put into MOS film recently, to process multiple lattices. It's always easier with a single lattice. And the last point is, when you've looked at your images, ask yourself, should I continue with this and struggle perhaps? Or should I just throw these data away and collect something off another crystal? Also, as Phil said, check two images at 90 degrees to each other, because very often crystal pathologies that you see in one orientation are not apparent in another, because crystals are not generally isotropic. Okay, then before you start to process, use the program tools to mask things like the backstop, the crystallography and other shadows. That's really because it's much, much easier to do in the integration programs than in the scaling programs. Now, Phil's put stuff into Scala and presumably also Aimless for masking out. Oh no, in Aimless he hasn't bothered. Okay. In Scala, there were tools for masking out duff regions of the detector. It's really hard to do that when you've just got a list of reflections to work with and you haven't got images to see where the bad regions are on your images. To do that. When I'm processing data, I always set the resolution limit to about 0.2 angstroms further out than I can actually see spots, which is very often useful information there. And increasing that limit a little bit will not disturb the integration. It won't go badly. The refinement won't go badly because you've got a little bit of extra information there. Okay, make sure the beam position is more or less correct. If the beam position is wrong, you won't be able to index in the first place, and it just makes life impossible at that point. And then have a look at the other parameters. Make sure the distance and the wavelength and rotation angle and so on that are reported by the program correspond to what you think you collected. I've seen images from a small synchrotron in the southeast of France where all the useful information in the image headers was wrong. So the beam center, the distance, the wavelength was all wrong because what they'd done is they'd moved a detector from one beam line to another and nobody had bothered saying, hey, let's update the headers. And it's only because the user had actually written down the numbers that we're able to rescue the data. It doesn't happen very often, but it does happen. Okay. That's the kind of political talk to make sure you do things right before you start. To take data processing as a whole, you can divide it into the stages. On the right-hand side, I've put down listed the programs that we use in the CCP4 paradigm for processing the data. We've got the data reduction, where we do the indexing, the parameter refinement, and the integration itself. In other words, the measurement of the spots on the detector. We use MOS film. We can check the symmetry and get the Lowy group out, and maybe the space group if we're lucky. Use pointless. Following that, we scale and merge together the reflections that we've obtained from MOS film to both merge the partials together to form complete reflections and also to merge together symmetry equivalent reflections. And there's a caveat to that second point that I'll come to later. And then finally, we do this process of truncation when we move from F squareds or intensities to F values. And in that process of truncation, we analyse the intensity distribution, and you can start to look at pathologies that may be associated with your data. So, what does indexing do? Well, it gives us approximations to, and they're actually pretty good approximations. You can normally process your whole data using these approximations, but they're not as accurate as they could be. But we get the unit cell dimensions, we get the crystal orientation out from auto-indexing. And mathematically we can combine these together in the orientation matrix. And there are different ways of expressing the orientation matrix, and I'm not going to talk about them anymore today, but I'm going to try to avoid as much maths as I can. And we can also get a first estimate of the Bravais lattice. So any of the programs that you use for indexing will give you an indication of the likely Bravais lattices for the crystal you're looking at from the indexing. But there are two things that the indexing gives us that are important. First of all, knowing the unit cell dimensions and the crystal orientation, we can work out where the spots on the detector are so that we can measure them accurately. And you might think this is a kind of a bit of a circular process because we need to know where the spots are to index, but we need to index so we know where the spots are. But that's more philosophical, I suppose. But the other thing is that unit cell dimensions are used in structure solution, in refinement, in model building and analysis. So we do need to have accurate values for those at some point. If we've only got low resolution data, what we get from indexing is probably as good as we'll get from for the unit cell dimensions. If we've got high resolution data, then we can refine these parameters and get much better values for them. Okay, so an overview of what we do in indexing is, first of all, you have to find the spots on the image, and this is actually quite a slow process, but we can do it reasonably efficiently. Then we take those spot coordinates on the image and convert them via a little bit of algebra to scattering vectors, which correspond to three-dimensional reciprocal lattice coordinates. Then, taking those three-dimensional scattering vectors, we can actually do the indexing itself. And the indexing itself is something that for many, many years was a real stumbling block for a lot of processing because there weren't good methods for indexing about until the early 1990s. And then when indexing became easy, it became much easier for the whole of the rest of the process, for the refinement, for the integration, and everything else flowed on much more easily at that point. Cell reduction is merely the process of trying to find the appropriate triclinic cell that has angles as close to orthogonal as possible with as small cell edges that account for the spots on the image. Then we apply Bravais lattice symmetry in any of the indexing programs, and that's when you get an idea of whether you've got higher symmetry than triclinic. So if you've got monoclinic, orthorhombic, trigonal, tetragonal, whatever. Now, either the program can pick a solution at that time, or you can pick one. It takes a little bit of experience to know what a good solution looks like, but most of the indexing programs will have some kind of penalty function that will give you an indication of what is a good solution, what is a bad solution. And then it's useful, following that, to get an idea of what the mosaic spread of your crystal. And that's very useful because the refinement and the integration make use of that information. And then, as I say, the indexing just gives us an approximate solution, and we hope it'll be good enough to proceed. The way to check that is actually to look at the predictions the programs give you superimposed on your images. And you want to make sure that the predictions actually do lie over the spots, the diffraction spots that appear on your image. Okay, this is about the only maths I'm going to have on here. Basically, we can take the 2D image coordinate of the spots and we can convert them to scattering vectors through that equation. Basically, what we've got here is a Pythagoras in 3 dimensions. We're just doing a little bit of trigonometry there. But in order for this to work properly, we do need to know the wavelength, we need to know the crystal detector distance, and we need to know the beam centre very accurately. Otherwise, the conversion to 3D coordinates, which is based around where the beam centre is, will be incorrect, and the chances are the indexing will not work. Right. One or two of the previous speakers have mentioned the Awald sphere. And it's something that does cause a lot of problems because it can be quite hard to understand. The Awald sphere is a construction that's there to help you understand what's going on. The Awell sphere doesn't really exist in the real world. So if you don't understand it, don't worry too much about it. However, imagine you have a detector over here that has 8 diffraction spots appearing on it. We can project those back onto the Awell sphere, and as we know, when a reciprocal lattice point is on the Awell sphere, you get diffractions. What we're going here is from the diffraction. Right. From the diffraction pattern to the reciprocal lattice impinging on the Awell sphere. If we have a direct space lattice edge parallel with X here, and we project these points onto that edge, then they will line up in constructively to give us peaks at different points. So at this place, circle on the Awell sphere, they will all line up here. If we have other spots that cross the Awell sphere further along, they'll be a little bit further along that unit, that vector. If you have a set of regularly spaced peaks arising from these points on the vector, then because Fourier transforms are particularly good at picking out regular features, you'll get large peaks in a Fourier transform. The first plot is a plot of scattering vectors projected onto a unit cell, a real space unit cell axis. And you can see that the peaks there are very nicely and evenly spaced. If we calculate a Fourier transform with that, we get another set of evenly spaced peaks, but they decrease in height. In the auto-indexing that we use in MOSFilm, all we do is we take that first big peak, and that corresponds to a real space unit cell edge. In this case, it's about 68 angstroms. Now, if a single image has 3 information from all 3 dimensions, then it's quite possible to index the 3-dimensional unit cell from just a single image. Occasionally, if you get a unit cell edge that is aligned along the X-ray axis, information from that cell edge will not be present in the image, and you may need to process using index off 2 images. Okay. Okay. Indexing itself will only give us the shape of the cell, or the geometry. And the basis solution that MOSFilm or any of the other programs give you is a triclinic solution. And there are a set of 44 different symmetry transformations that can be applied to that triclinic solution to see if there is any higher symmetry solution that corresponds to this triclinic cell. And these are tabulated in international tables. One of the things you notice with the programs, there are some programs will give you a huge, great list of 44 solutions, and other programs will only give you a shortened list. What I have noticed occasionally with running Denso for the auto-index or HKL is that because there are two solutions with the same Bravais lattice symmetry with very close penalties in the calculations, sometimes the program will pick the wrong one. And because you only get the 14 best solutions that the program's decided on displayed in the output, you can often miss the wrong you can sometimes rather miss the right solution. I like the MOSFilm and XDS way of doing it because you get a full list and you can work through them if you need to. One of the things about the solutions that MOSFilm gives you in the indexing is it does try to pick what the program thinks is the appropriate Bravais lattice symmetry. Now, very often that's right, but sometimes MOSFEM will be over-optimistic in the solution it's chosen, so it'll try to apply too high a symmetry. Sometimes if your parameters are wrong, say your crystal detector distance, your beam centre are wrong, then it'll pick a solution that has too low symmetry. And very often you can see things like that happening when you don't get a big jump in the penalty from good solutions to bad solutions. The last point is, bear in mind that the space group that you obtain from auto-indexing is only a hypothesis until you've solved and refined your structure and possibly even submitted it in the PDB. And even then, there are quite a number of structures with the incorrect space groups. In the small molecule database, there was a study done in 1990 by a guy called Dick Marsh, who looked at 1,500 structures, or with like in one of the monoclinic C-centered space groups, and found that of the 1,500 structures he looked at, 144 were wrongly assigned as far as the space group went. So that's nearly 10%. Assigning the wrong space group does not mean that you can't solve the structure. You can very often solve the structure, but there are odd things about it. You may have multiple copies in the asymmetric unit. You may have multiple copies in the unit cell that where the unit cell is too big. You may have the unit cell that's too small. However, remember, it is a hypothesis. You can always go back and reprocess your data in a different symmetry should you need to. Okay, now the Bravais lattice from intensities. By analysing the distribution of spots on your image, you can't actually work out the Bravais lattice symmetry. For example, I've got a representation of a reciprocal lattice in the precession geometry that's been produced down a particular axis from a data set that Phil and I were sent some years ago, and the user having a lot of trouble with it. From the what are written on the right, you can see this should be orthorhombic C-centered, but from the distribution of the spots in space, there's no way of telling that at all. The only way you can tell this is if you look at the distribution of intensities of the spots. And so you can only do that after you've done some measurement of intensities. And you can see that the apparent hexagonal symmetry I had in the first image disappears very quickly when you look at a zone. I think is that the HOL zone? No, one of the major zones in the data. Yeah, sorry. Yeah, and you can see quite plainly that there is a twofold symmetry there and twofold symmetry there, and there is no sixfold symmetry in the apparent hexagonal sixfold axis.
Why is the hexagonal C-axis? Well, the apparent hexagonal.
It's apparent because the cell edges are accidentally could be transformed to give you a hexagonal cell edge.
Yes. E is root 3 times A or something.
Yes, I haven't written that down there. Yeah. Okay, so take note of the intensities and remember that the Bravais lattice you get from indexing may not be correct because the indexing pays no account to the intensities that you have. Okay, I said earlier that indexing only gives you approximations to the values. And what we have to do is we want to refine these parameters that we've obtained from the indexing and also our machine parameters as well, which may not be very close to their true values. The refining parameters is merely the optimization of the fit of the observed to the predicted spot positions, so that when we come to the integration, we can put our measurement boxes over the spot positions. In other words, we can accurately locate the spot positions and measure what's actually where we want it to be measured. Two things we do here. We improve the estimate of the crystal parameters, the cell parameters, and the crystal orientation, and also the instrument parameters, things like the crystal to detector distance, the direct beam position on the images, the tilt and the twist of the detector, and things like that. as I said before, accurate cell dimensions are important because they are used in all subsequent stages of structure determination. And we can perform this refinement process either by a positional refinement, which uses the spot coordinates on the detector, which is fairly easy to understand, and most people can work that out fairly quickly, or get a handle on it fairly quickly. Or we can use post-refinement using intensity measurements. And it's called post-refinement because it can only be done after you've got an estimate of the intensities of the spots. So this just really expands a little bit on the previous slide. So with positional refinement, we use the spot positions on the image. And so what we can do is, for each individual image, you can run a positional refinement. And this is done in a lot of the programs that process data. And we can use both fully recorded reflections and partially recorded reflections. If you collect data at a synchrotron these days, mostly you won't ever get any fully recorded reflections. So you'll just be using partially recorded reflections for that. But post-refinement needs intensity measurements that are spread over at least 2 images. And we can't use any fully recorded reflections for that. And this is a good reason not to collect coarse slice data too often if you can help it, because it reduces the number of spots on the images that you have available for post-refinement. Okay, as I said, we need to have 2 images, probably more when we've got very fine fire slicing, but not too many. Okay, this is just an image with spot positions, which are in black, and the predicted boxes, which are all off to one side. And you can see that what we want to do is we want to shift our parameters so that all of the measurement boxes move kind of down and to the left a bit. What else can I say about that? That's what you have to do, and it has to be done mathematically. And there are some parameters you can alter in your model in order to do that. Mathematically, what we're doing is minimising these things. That's the difference between the calculated and observed positions horizontally in X and calculated and observed positions in Y, so vertically on the detector. And we square these and just try to minimise that sum. Now, if you remember that your crystal is mounted on some kind of axis, which routinely we call the phi axis. Sometimes if you have a multi-circle goniostat, it'll be on the omega axis. But rotating the crystal about that axis has no effect at all on this residual, so you can't refine the angle of the phi axis through this method. The cell dimensions and other parameters, particularly the crystal to detector distance at low resolution, can be very strongly correlated. So you have to be very careful about refining things like the crystal detector distance and the cell dimensions simultaneously. There are some programs force you to do this, essentially, or to fix one and refine the other, and do them in cycles. It can lead to instabilities in the refinement and bad results. However, what I've got here is a list of the parameters that can be refined via positional refinement. So we can refine the unit cell dimensions, we can refine crystal to detector distance, bearing in mind that caveat. The Y scale, which is the apparent size of the pixels in one dimension compared to another dimension. Not all detectors have square pixels. We can refine two of the 3 crystal missetting angles. We can refine the detector missetting angles, so in other words, the tilt and the twist and the rotation, and also the direct beam position. Now, post-refinement, or the bicentroid method, uses the apparent intensities of partials spread across several images. I've got 3 consecutive images from one of our kind of favourite data sets here. You can see that this reflection is strongly on the first image, it's a little bit weaker on the next, and not there at all on the third. By taking account the apparent intensity on that image and on that image, you can work out that the true centroid for that reflection is probably somewhere during that exposure, because it's a little bit stronger on that image than on that. There's another spot down here on the left-hand side where there's no apparent intensity there. There's a lot of intensity on the central image, and there's just a tiny little bit of intensity there. And so the phi centroid of that reflection is probably somewhere just after the midpoint of that image. And we can do this for many reflections. But mathematically, all we're doing is, again, very similar to the one we did for the positional refinement. We take the calculated position of the reflection, the observed position, divide it by the apparent resolution of that reflection, the sum, and try to minimise that sum. But we do need to have a reasonable model of the intensities for that. And so we can only do it after some integration, hence post-refinement. We also need a model for the rocking curve. And the rocking curve is a model of how the intensity of a spot changes as it passes through the reflecting condition. In other words, how that reciprocal lattice point is passing through the A-Weld sphere. And various rocking curves are being used, and it doesn't really seem to make much difference what model rocking curve you use for this. But again, we can use it to refine the unit cell dimensions, just as we could in positional refinement. 2 of the 3 crystal missetting angles, which are not the same, which do not coincide with the 2 or 3 with a positional refinement. And we can refine either the mosaicity or the beam divergence. And that's because the beam divergence and the mosaicity are very closely correlated in the way we do the refinement. So usually we have to fix one and just refine the other. You can think about this again in the A-Weld sphere construction, so that if we have a calculated position for our spot and an observed position for our spot that has some value for R with a known resolution, we can minimise the delta by the sum I showed you on the previous slide. Okay, so that's the refinement. We move on to integration. There are 2 basic ways you can do integration. Summation integration, which is very fast. All you're doing is counting up the pixels on the spot for each spot on the detector. Or profile fitting, when you try to fit some sort of model to the shape of the spots on the detector to try to improve their measurement somehow. And that's only actually intended to improve the measurement of weak spots where their backgrounds are sitting, the shoulders of the spot are sitting underneath the background on the detector. And further, you can subdivide that into 2-dimensional integration, which is what MOSFilm does, where it measures intensities on each image individually, and then we combine them later. Or 3D integration, which is what programs like XDS do, where they try to build up a fully recorded reflection as the integration proceeds. And that may have advantages, it may not. Certainly in my experience, there's no real difference in the results you get from the 2 methods. But 3D integration may be more intuitively correct, if you like. Okay. But when you're measuring the intensity of a spot, first of all, you ought to work out where the spot is and where the background is as well. And bear in mind that if you've got background out here and all around here, then you also have background sitting under the spot as well. So but you can never measure the background directly that's sitting under a spot. So you have to try to work out from the adjacent background what the background is likely to be sitting under the spot, so you can subtract that from your measurement. Of course, if you have no background at all, you can locate your spot, just add up the pixel counts that are there, and hey presto, that's your intensity. If you look at data sets collected with Pilatus detectors with fairly short exposures, very often these days you will see you get 0 counts in your background. And summation integration is what we do for processing Pilatus images mostly. We still need to define the spot and the background regions. As I said, we can't measure the background directly under the spots. So we calculate a local background plane and a slope from nearby non-spot pixels. So we don't have a rough background. We calculate the background as being a smooth plane that is at some angle to the overall background that's on the image. And the weak spots may still, even on a Pilatus, have their shoulders under a background, and their measurement is impaired because of this. And that's why we use profile fitting. And profile fitting is based on the assumption that spots corresponding to fully recorded spots in the same region of the detector, and also on images that are nearby in size, so the image before and the image after, have got similar profiles. Now, if you look at this image from a CCD detector, you can see we've got a nice, strong reflection up here that appears to be quite big on the detector, where it has other reflections near it by, which look smaller. The reason why they look smaller in the display is because their shoulders have disappeared below the background level. And so it's like an iceberg poking out of the sea. You only can see that part of it that is poking out, and most of it is still sitting below. In profile fitting, what we do is we have to work out what our profiles are going to be. So we use what are known as standard profiles. So we find some good, strong spots that aren't overloaded, aren't too weak, and calculate an average profile for what those spots would be if we normalised their intensity. But what we need to do is we need to be able to place our profiles accurately to within about 1/10 of a pixel or so. What this does, if we apply these profiles to our reflections, is that for the weak reflections, we improve the variance estimates substantially. And as a consequence of that, we should reduce the random error from our weak reflections, but with very strong reflections, it can increase the systematic error associated with them. Okay, the profiles vary. They can be different in different areas of the detector. If you've done the practical with our HIP-F data and looked at the profile regions, you'll notice that there are some regions where our profiles are distinctly different from where they are in other regions. And usually you get nicer profiles towards the centre of the detector than you do out towards the edge. Profiles will spread out due to obliquity of incidence towards the edge of the detector anyway. But the important thing is that mostly profiles don't vary very much across the detector, and they don't vary very much from one image to the next. And so, for example, in loss film, we often use the same profiles over batches of images, say 10 or 12 images. There are other things that profile fitting can do to improve our data. What you can do is you can identify spots that don't fit the expected shapes that you get. For example, you can identify zingers, which are very often put down as being cosmic ray incidents or radioactive decay incidents, whatever. Zinger comes from a Canadian statistician who published on outlier detection in the 1950s. Or you can identify overloads. There are a lot of the CCD detectors, for example, kind of bleed out from the edges of the spots when they're overloaded. And the shape changes. And so you can use your calculated profile to estimate what the intensity of that spot should have been had it not been overloaded. And you can rescue some data like that. It's better not to overload spots if you can help it. So, when you're analysing the results of integration, in any of the programs these days you'll get a lot of graphs. Basically what you're looking for is graphs that vary smoothly, without obvious discontinuities, without plots that go up and down wildly. If you get large changes in parameters, they can indicate problems with either the crystal. The crystal may be decaying, it may be moving in or out of the beam. There may be something wrong with the instrument that's being used to collect the data on. And then when you find discontinuities in the graphs, have a look at the images that are associated with those discontinuities. It can be very revealing. What I think is that the I over sigma I at the high resolution limit, less about 0.2 angstroms. So say if you have a 2.4 angstrom data set, have a look at the intensities at about 2.6 angstrom. And the average I over sig I, for a reasonably well collected data set, should be greater than about 1. And about 1, it's very hard to be prescriptive about these numbers. Different people have different opinions about them. Also, any program that encounters any problems will issue some kind of warnings. If you look at the old MOSFilm log file, you'll see that it will very often give you a lot of warnings about things that have gone wrong in your data processing. If the processing has gone to completion, then these are usually not terribly serious warnings, and I tend to view them more as information rather than as warnings. People do get very worried when the program issues 20 or 30 warnings at them. MOSFilm can be a bit fussy like that, but the serious warnings in the log file are all associated with advice on how to get rid of the warning, how to reprocess your data, taking into account the effects that have given rise to those warnings. Other programs I can't speak for quite so well. This is kind of our favourite test data set. Basically, the graphs that are plotted by default are nice and smooth, but there's something odd happening around image 75 there. And it's the sort of thing that if everything else has gone really well and suddenly there's something not looking quite right, it's worthwhile having a look at the images around there to see what's caused that. And because the post-refinement, which is all these are the parameters that are refined by post-refinement, those parameters by positional refinement, because these parameters are using information from several images in the refinement, it may not be the first image that is associated with the discontinuity that's given rise to the problem, that's given rise to the discontinuity. Okay, scaling and merging. Scaling and merging the data is very important because it puts all your observations onto a common scale so that you can use them in any subsequent analysis. Also, it does give you the main diagnostics of the data quality and whether the data collection is satisfactory. And the statistics you get out of MOSFilm or out of the integration programs are useful, but not as useful as those you get from the scaling, because they tend to be working on individual images and how they're varying through the data collection, rather than looking at the data set as a whole, which is where the analysis from the scaling and merging step comes. So, when possible, if you can scale your data while it's still sitting on the X-ray camera, before you've dismounted it, before you put it back into the Dewar, have a look at the scaling and merging statistics, and if there are any problems, you then can very easily perhaps collecting more data or collect better data, collect the data in a slightly different way. And for that reason, it's a good idea to be integrating and processing your data while you're actually collecting it. And that gets harder and harder as data collection gets faster and faster. But it's still worthwhile doing. As I said right at the start, it's your experiment. You may have taken months or years to get to the point of having a crystal that you're collecting. Okay, but we're still talking about scaling. So why are the reflections on different scales in the first place? Well, there are three groups of factors that give rise to this. You've got the incident beam, in other words, the beam that's shining on your crystal, and the camera. And the camera is basically the detector, the goniostat, the monochromator, everything that is mechanical that isn't your crystal in the experiment. Okay, reflections are also on different scales because of the crystal and the diffracted beam, the beams that are coming out of the crystal, and problems with the detector, right? Effects due to the detector. Now, all the integration programs, I think, apply the Lorentz and polarization corrections because we know those from the diffraction geometry, and there's simply no need to take those into the scaling program under most circumstances. Okay, but other factors aren't taken into account in the integration programs. And what we're really kind of trying to do with the scaling model is we're trying to parameterize the experiment. We're trying to divide up the experiment's parts so we can account for the changing effects of each of those parameters during the course of the experiment. And of course, a different experiment may require a different model. And that's kind of where the expertise of the kind of the programmer for the scaling program comes in. And then the last point, understanding the effect of the factors can give you a sensible design of the scaling program. Okay, looking at those three factors, okay, with the incident beam and the camera, variable incident beam intensity. Now, on most lab sources, this isn't a big problem. On synchrotrons, it used to be a big problem when you get the beam decaying away. It's not such a problem nowadays with modern sources. The illuminated volume of the crystal. Sometimes your crystal isn't accurately centered in the beam, and as it rotates, it moves into or out of the beam. And that can give a rise to different intensities from the crystal just because its orientation has changed. Also, absorption in the primary beam by the crystal. So if you've got a very heavily absorbing crystal, you can get problems that are very hard to distinguish from the changes in the illuminated volume of the crystal. But back in the days when I was doing small molecule work, I collected or did some photography, X-ray photography, on a crystal that was very large and had a lot of very third-row transition metals in it. And the spots from the diffraction were basically donuts, where the X-rays hadn't managed to get all the way through the crystal in the middle. It's not something that we would ever come across in our sort of work now. Okay. Sorry? Yeah, it's just absorption in the middle of the crystal. And so the beam could get through the outside of the crystal, but it was completely absorbed by the kind of, it was about 0.5 millimetre, 1 millimetre. It's a huge crystal. Sorry. Okay. If the rotation speed on your phi axis is uneven, so if it's not smoothly rotating, you can get real problems. And with CCD detectors, you also have to synchronise the shutter accurately so that it opens accurately at the start of your rotation and closes precisely at the end of the rotation, so you get even exposures for every image. And synchronisation errors like that can cause real problems in the processing. With a Pilatus, that's not a problem because we just keep the shutter open throughout the whole exposures for the experiment. If you've got machine instabilities with similar time periods to the exposure, you can still get problems on the Pilatus data sets. So things like crystal vibrating because of the cryojet if you don't have a sufficiently rigid pin that the crystal is mounted on, for example. Okay. The second factors are due to the crystal and the diffracted beam, so absorption in the secondary beam. If you've got a long wavelength data set, for example in the home source on copper K alpha, and you've got a big crystal or you've got some heavy atoms there, this can be a big problem. Radiation damage, again, is something you tend not to see so much on home sources. I think on the FRE downstairs people do see it. Okay. Unless you've only got small changes, this can be very difficult to correct for. Also, of course, as your crystal is changing, the structure of the molecules inside it are changing as well. So you may want to stop your data collection before you get too far. Extrapolation back to zero time was popular a few years ago. I don't know if people do it. No.
If you need high multiplicity, then you will have more radiation damage.
Yeah, unless you really reduce your exposure time.
Yeah. You cannot have high multiplicity.
Yeah. This is why you need to design your experiment, because the data collection is an experiment. Okay, and then the detector. Now, you say the detector should be calibrated properly. This is done pretty effectively by the manufacturers, so it's not something that we really need to worry about at our stage. If we notice problems at our stage of using the detectors, then it's something we should tell the manufacturers about, I think. In the corners of in multi-module detectors, particularly for big CCDs, did you say there was a problem with Pilatus earlier or not, Phil? No. Okay. So scratch that. Only for CCDs, not for Pilatus. The measurement, you get anomalously high measurements in the corners? Right, anomalously weak reflections, yes. And Phil's been working on this for some years to try to come up with a good correction for it.
Failed utterly.
So far, yes.
Okay. Okay. All detectors have got bad pixels on them. So that some of them, there are some pixels on a detector will be hot pixels. They'll always get an anomalously high reading from them. Some just don't seem to respond to X-rays hitting them, and they're cold detectors, or just dead. All the detectors, again, that are built up from tiles actually have gaps between the tiles, and you can't measure anything if your photons hit between the gaps. And Pilatus has got an 8% dead area because of the gaps between the tiles. And that's a shortcoming that people manage to get around, but it's still not desirable. I said that to begin with, that you should tell the integration program about obstructions, because the scaling programs can no longer do that. Okay. But what are we doing in scaling? We're trying to make the symmetry related and duplicate measurements for reflection equal by modelling this experiment, so taking into account all of these different factors. And what scaling is trying to do is to make the data internally consistent. It's not trying to apply any extra kind of model to the data to make it fit anything else. But it is minimising the differences between the individual observations and their symmetry equivalents. So if there are systematic errors that arise from other sources, then scaling will not take care of those errors. Once reflections are on a common scale, we want to do two things. We merge together the individual parts of partially recorded reflections to get fully recorded, complete reflections. And we also want to merge together symmetry-related reflections into unique observations. For example, for monoclinic, we want to merge together the HKL and the bar HK bar L, or for orthorhombic, these reflections are related by twofold axes, etc. And if we're not looking for an anomalous signal, also the Friedel pairs or Friedel mates, both terms are used, where we merge together reflections HKL and bar H bar K bar L. But, as I said, if you're doing any anomalous experiment, if you merge Friedel pairs, you may as well not bother. Also, some programs, for example, the shell XCDE pipeline, prefer you not to merge your symmetry equivalents together because George Sheldrick thinks that he wants to do it his way for his programs, basically. I'm sure Andrea could comment on that. Okay.
I think George can comment on that in September.
Okay, right. Okay, so questions about the data. Basically, these are the sort of things you should always ask when you get to the end of your data processing. So, what is the overall quality of the data set? If you've got other crystals in the same project, how does it compare? Have you got a complete data set, or do you need to collect more data in order to get a complete data set? A complete data set will give you a better structure, it gives you more 3D information. And what's the multiplicity? Generally speaking, higher multiplicity is a good thing because you're more sure of the quality of the individual data points. Okay? Find out what the real resolution is. Very often you will see from scaled and merged data that you have a higher resolution data than you can actually see spots on your diffraction images. Alternatively, you may be trying to process to too high resolution and have no information in the high resolution regions, so maybe cut back the processing to lower resolution. Have you got bad batches? Are there individual images, or are there groups of images that are bad? Have a look at the images and see why that's happened. Is the whole data set bad? Sometimes the best thing you can do is just throw it away and not waste time on it. Have you got radiation damage? Should maybe you just use the first part of the data? Is the outlier detector working well? So are there odd reflections that you can identify that are grouped together in particular parts of the detector, for example, say round ice rings or near a backstop arm? If you want an anomalous signal, can you see one there? And are the data twinned? Which is another problem. How am I doing? Okay, another 5?
Yeah.
Okay. Okay. This is kind of the table 1 that you get out of, I think this is probably from Aimless rather than Scala. But basically, what you want to look is to know what the numbers should be like for good data sets. And you can discuss with other people in the lab. I don't want to talk too much about that, except that overall, you'd expect the values to be a bit higher than for the inner shell. The values for the inner shell data should be very good, and in the outer shell, they should be verging on the marginal and getting sort of reasonably bad values. And I don't want to discuss too much about what actual values you... It was one of your data sets, Phil. It can't be too good.
It's an in-house data set.
Yeah. Anyway, I'm not going to talk about what actual numbers you get at the moment because I simply don't have time today. And this is the second half of the bottom of that table, which will give you some idea about what the program thinks the resolution limit is, the real resolution of your data. And we'll also summarise things like the unit cell and the space group, the average Mohs things like that, and the correction factors that the program has applied to the data in order to get things onto a common scale.
It's the SD correction.
Yeah.
There's the fudge factors on the standard deviations.
You heard it from the man himself. Okay. Following scaling and merging, you have truncation, and basically what truncation is doing, it's analysing the scaled and merged data according to an expected physical model. That was first looked at in the 1940s. But it gives you statistics on intensity distributions, and the two I'm going to just mention very briefly are the Wilson statistics and twinning analyses. And as far as the CCP4 programs are concerned, it also outputs F values for use in the subsequent CCP4 programs. Again, this is something that George Sheldrick has been banging on about for about 30 years, saying that we shouldn't be using F, we should be using F squared values. But more of that in a later talk. Okay, so the Wilson plot is basically dividing up the data into resolution shells and taking the mean value for the intensity in resolution shells and using the sum of the individual scattering factors for the atoms squared that make up your crystal, summing those, taking the log of that, and plotting it against this rather odd-looking way of expressing the resolution. It's just that when you express the resolution like that, if you draw out that plot, if you have a structure that has randomly distributed equal-sized atoms in your cell, you get a straight line out with a slope of -2b, where b is the Wilson B factor, which is an estimate of the isotropic temperature factor of the structure. It's something you can look at to get an idea of how well your crystal is actually diffracted. However, protein crystals don't have randomly distributed atoms. You've got features in them, things like alpha helices and beta sheets, and solvent as well takes up a large part of the cell. So we don't get a straight line for Wilson plots with proteins. What you do is you get something like this that has a nice big dip at around 5.5 angstroms or so. But this part of the plot is reasonably linear, and that part of the plot is what's used for calculating the Wilson B factor. If you've got more disorder in the crystal, you get a faster fall off with intensity, and so the B factor increases. It's a negative relationship. Okay. And we use what we call normalised intensities, which are the intensities that we would get if the atoms were at rest. Okay, very briefly, a slide I kind of cribbed from one of Andrea's again on twinning. If you have two crystals that have essentially grown together with a very specific orientation between them, it's the phenomenon we call twinning, and it can give rise to very odd distributions of the intensities. And you can visualise this. So say if you take a projection of intensities from two crystals, where the right-hand one has been rotated round 180 degrees from the left-hand one, and superimpose the intensities that you get from the two components on each other, you see that you get a very strong reflection here is not found over here. It's much weaker. And this kind of averaging of intensity is one of the features that arises from merahedral twinning.
They are mirror images.
Two full symmetry are parallel to a plane.
Yeah. Yeah. Sorry, I was doing a 180 degrees that way. Sorry, I was doing a 3D projection from a 2D image, Andrea. You'd only get mirror images if you had a racemic. Okay, you can see that in the cumulative intensity plots. You can see it in plots of IO. Sorry, the mean value of I to the n over the mean value of IN, or for the normalised structure factors against resolution. These are the moments. So when you see the plots in the CCP4I of the second, third or fourth moments, what it's talking about is that exponent there, the IN, in those plots. I think I've gone on long enough. Finally, this is the thing. Don't expect the software correct for a badly performed experiment. As we keep saying, it is an experiment. It's the last experimental bit. All this computation stuff, you can go away and you can do again and again and again on your images. But if you've got crap when you start off with, you won't get a golden goose out of the end of it. You can't make a silk purse out of a sow's ear. Take the time to have a look at your images and the results of the integration and the scaling. And although you get some stats from the integration step, It is the scaling and merging step that gives you the best stats on the quality of your data. And I think at that point, I'll stop.
Tom, thank you. It was very interesting, useful. I think
Okay.
this is the important step that I said. Any questions to Harin?
Oh, good.
No, I have it. So a few questions. Thank you.
I'll talk to you later.
No, I think it is important to mention to the other, when you, if you can, you should keep a anomalous difference, the plus and the minus separate, because later you may use it to identify heavy metals and so on.
Programs never lose them.
Yes, before they are not never lost, but other programs you may.
Yeah.
Good.
Yeah, I'd agree with that.
No, I was hoping that you will continue on that.
I think people have heard enough of me for the moment.
So, any more questions?